This video serves as a quick visualization of the central limit theorem. This is not a proof, but simply a way to visually show that it works. In short, the central limit theorem states that, as more and more large enough samples are taken from the same distribution, regardless of the distribution, the sample means will be distributed normally. This may or may not seem intuitive, so let's look at two examples of this. First, with a uniform distribution. Here's a simple one, the continuous uniform distribution from -4 to 4. Let's take a random sample of 40 points from this distribution. I'm picking 40 for two reasons. For one, it fits nicely into a 10-row, 4-column grid so that you can see these first 40 samples. And two, 40 is greater than 30. We'll get into that soon. We find that the mean of this first sample is -0.44. Now let's move this uniform distribution up and draw a normal curve plotting the sample mean of ours. We can now take a bunch of samples of 40 numbers each. For tracking purposes, you'll see each of these samples appear on the uniform distribution, their means plotted on the larger graph, and also tracked with a histogram, and the mean placed in the grid on the right. Just so there's no confusion about what I'm doing here, all I'm doing is grabbing 75 samples of 40 values each and then plotting their mean on this graph with the normal curve. You'll see that as more and more samples are taken, we get a normal-ish looking histogram. To show this mathematically, let's consider the main parts of the normal distribution, those being that the mean and median are equal, and that the distribution is symmetric around the mean. In other words, the left side is equally as dense as the right. What do we see? First, we see that our mean and median are pretty close, roughly equal. We can also see that around 45% of the distribution is left of the mean, whereas 55% is to the right. With 75 sample means, we can see that the distribution is roughly normal. The more samples we take, the closer the distribution will get to a normal one. Maybe this example was helpful, maybe it wasn't. Let's do another, far less obvious one. Here's the exponential distribution, entirely skewed, not even remotely close to uniform or normal. Just as before, let's grab a random sample of 40 points and take their average. That average is just about 1. Again, let's draw a normal distribution and begin plotting and tracking 75 sample means. Now, the reason I wanted a sample size greater than 30 is because 30 is generally considered a large enough sample for the central limit theorem to kick in. When your stats teachers or professors tell you about sample sizes greater than 30 being approximately normal, the central limit theorem is where they're getting that number from. It allows you to better predict how probable a sample with that mean and variance are. Now, at first, this might not seem normal at all. I mean, it's not even close to the center of our standard normal distribution, but let's remember our requirements. First, we see that our mean and median are nearly equal, close to 1. Then we see that our samples are, again, nearly symmetric around the mean. This gives us another approximately normal distribution. As you might expect, the more samples that we take, the closer we get to a normal distribution. Hopefully this has been a helpful explanation, although not very mathematically rigorous. If you're still not quite seeing it, I've created an additional animation for both of these distributions, but instead of 75 samples of 40 points each, we pick 150 samples of 50 points each. That should hopefully help you visualize how the central limit theorem works.